Hello students, very good afternoon. This is Mayur S. More, your chemistry tutor. As you all know, NEET exam has been scheduled on 12th of September, right? So we all are preparing for NEET exam and practically has brought exclusive a NEET crash course for you where we'll be covering the chemistry chapters which you have for your syllabus. Okay, we will be covering that for 20 days, out of which we have already covered the 11th session. Today we are in the 12th session of our NEET crash course, where we are covering a chapter called coordination compounds. This chapter has a really high weightage. This chapter has really high weightage and it is the most important chapter of your inorganic chemistry. Okay, so this is Mayur S. More. Welcome you all. Very good afternoon. Let's begin. So, what is the IUPAC name of this complex? Now, whenever we are writing a IUPAC name, see, you always need to name the ligands according to alphabetical order. Now, what are the ligands? The negatively charged species or the species having a lone pair which are present inside the coordination sphere are called as ligands. And we indicate ligand by L. So this is ligand. This is also ligand. This is not ligand. This is your complementary ion. So this is chloride, right? And this is aqua. Now between chloride and aqua, which comes before in alphabetical order, we all know chloride. If you write chloride, it is CHO-Li, chloride, and aqua, AQA. So as we all know, we have learned the ABCD, right? A comes before the C. Therefore, while writing this name, you should write aqua first. Okay. So its name should be tetra aqua because there are 4 aqua group, no? Tetra aqua, dichloro. Then we also need to find out the oxidation state of your chromium here. So if you write the compound CrCl2 H2O4 and you have NO3. We all know NO3 has a -1 charge. So if the NO3 has -1 charge, nitrate, this compound will have a +1 charge. Okay. Then what is the oxidation state of chromium? Suppose chromium is X and chlorine is in a -1. So 2 chlorine, -2. Water is in a 0 oxidation state here. I mean, water does not have negative or positive oxidation state. Water is a neutral ligand. So X -2 +1. -2 goes on that side. You get X is equal to 1 + 2, which is equal to +3. So chromium has +3 oxidation state. So what should be its name? Tetra aqua. Tetra aqua dichloro. Chromium 3 nitrate. And that should be its IUPAC name. Okay, that's how you should name it. Okay, sure. Moving ahead, among TiF6 2 minus, COF6 3 minus, Cu2 Cl2, NiCl4 2 minus, the colorless species are. Let me tell you which species are colorless. For any species to be called as a colorless, it should either have 0 d electrons or it should have 10 d electrons. So D0, D10 systems are colorless. For your system to be colorless, it should be either D0 or it should be D10. Okay. So let's look at one by one how these species, how many species are colorless and how many of them are having a color. The first is TiF6 2 minus. Okay. We don't know what is the oxidation state of titanium, so we need to find that out. Then we need to find out how many d electrons your titanium has. Its atomic number is given, which is 22, right? So oxidation state of titanium is X. Each fluorine will be in a -1 charge, right? So 6 fluorine would be in a -6 charge is equal to overall charge. What is the overall charge? -2. So X is equal to -2 + 6. So 6 - 2, 4 is equal to +4. Therefore, titanium is present in a +4. Atomic number of titanium is 22. So its electronic configuration is argon 4s2 3d. So 4 electron has gone. That means this 2 electron has gone. This 2 electron has gone. So basically titanium 4 plus has 0 d electron. And therefore this has to be colorless. As I told you earlier, any species to be colorless, it should have a 0 d electrons or 10 d electrons. Okay. Next is COF6 3 minus. Now as far as COF6 3 minus is concerned, you can find out the oxidation state of cobalt here. It is X. 6 fluorine will have a -6 charge. We just saw is equal to overall charge on the species. The overall charge is -3. So X is equal to -3 plus 6. 6 minus 3 is equal to +3, right? So your cobalt is in a +3. Atomic number of cobalt is 27. So how would you write its electronic configuration? Cobalt 27, argon 4s2 3d7. So out of that, 3 electrons have gone. That means 2 electrons from S has gone and 1 electron from D has gone. That means it's a 3d6 system. So it has some d electrons. And since it has some d electrons, it cannot be colorless species. Okay. Third option, Cu2Cl2. In Cl2Cl2, what is the oxidation state of your copper? 2 copper are there. So 2x. Chlorine is what? -2. Because 1 chlorine is -1. 2 chlorine should be in a -2. What is the overall charge? 0. So 2x is equal to 2. Therefore, x is equal to +1. So each copper is in a +1. What is the atomic number of copper? 29, right? But the electronic configuration of copper is how? It is 29. It is argon 4s1 3d10. It has an exceptional electronic configuration, right? So 4s1 3d10 and copper is in a +1. So this +1 electron goes from the S. What remains is d10. So basically it's a d10 system, and d10 system is also colorless. That means out of these 3, TiF6 and Cu2Cl2 are colorless. And if you look at both these species are present in option D. Yeah, it is present in option D, and therefore this should be colorless species. Okay, so moving ahead. Next, which of the following complex cannot exhibit geometrical isomerism? See, geometrical isomerism, for any compound to show geometrical isomerism, it should have a system like this: M(A2)(B2), where A and B are what? A and B are ligands. They are ligands. And M is what? M is your metal, central metal, which is getting surrounded by ligands. So M(A2)(B2) system can show geometrical isomerism. Then M(A2)(BC) can show, here there are 2 same ligand and 2 different ligand, B and C. So this can show geometrical isomerism. M(A3)(B) cannot show geometrical isomerism, and M(A4) or an MB4 also cannot show geometrical isomerism. Okay, that's for sure. Now, if you look at all of these species, see NH3 2Cl2, this is M(A2)(BC) type. You can see here, there are 2 amine, 1 chlorine, 1 nitro. So this is M(A2)(BC), and it can show geometrical isomerism, that's for sure. PTGLY2. So PTGLY2, GLY is what? It's a glycine. It's a glycine, and there are 2 glycine. What is the structure for glycine? Glycine look like this, CH2, NH2. You have a C double bond O, O minus, right? So your platinum can attach from this side, oxygen from this side. Now, if you reverse it, if you reverse this platinum, or if this compound O minus C double bond O, CH2, NH2. So this, now this is trans, you can see here. Oxygen, oxygen are on the opposite side. NH2, NH2 are on the opposite side. So this is what? This is your trans, right? If you take oxygen, oxygen on the same side, or NH2, NH2 on the same side, it becomes cis. That means this can show geometrical isomerism. As we all know, cis and trans are nothing but what? Geometrical isomerism. Okay. Now, why this was happening? Because glycinate, this is your glycinate. Glycinate is a kind of a ligand. It's a bidentate ligand, right? It's a bidentate ligand. And how can we represent bidentate ligand? It's a bidentate ligand showing A and B. So your system is getting coordinated via A and B. There are two different atoms. As far as ethylene diamine is concerned, it is not AB type. It's a AA type. So if you write this, it should become like this, MAB2. Yeah. So this is how it can be represented. If you look at the option C, it would be represented like this, MAA plus. So that is your, that is the kind of a ligand which is having a same atom. So if I write it, let me show you. What is the long form of EN? EN is ethylene diamine. And ethylene diamine can be represented like this, N. So you can represent it like this. Now you tell me, even if I reverse this, even if I change this in any way, it can never become trans. It can never become trans. It is always a cis. So since it is always cis, it cannot be trans. That means it cannot show geometrical isomerism at all, right? So there is no question of it showing geometrical isomerism. That is why in this case, your answer should be C. Okay. Chalo, I hope you really enjoyed this. Now let's move ahead. Just a sec. I hope you are clear with this. Let me erase this because for the next question, you need to have this. You need to understand this. So I'll rub it down. Yeah. So I hope you are clear with this question. Now let's move ahead. Next question, CuH2O4 2 plus absorbs orange light. It absorbs orange light and transmitted a complementary color will be. So let me tell you color wheel. How does color wheel actually looks like? See, there are 7 colors. You all know, we had seen, we have studied as a kid those 7 colors from the rainbow, VIBGYOR. What do we call that as? Vibgyor. Now this Vibgyor can be placed. It can be casted in a color wheel. And I'm going to tell you the trick how to write the color wheel, how to reproduce it anytime, and how to check what could be your complementary color. Okay, see. So this is your circle. It may not look like a circle, I know, but anyways, they're not going to give us marks for our drawing. Okay, so these are 6 segments. Okay, you just need to ignore I, which is indigo. And you need to start putting V from here. So V, P, G, Y, O, and R. So whatever color, let me tell you, the color which are exactly opposite to each other, the color which are exactly opposite to each other are complementary color. That means if your compound absorbs red, it will be transmitting green. If it absorbs green, it will be transmitting a red. If it absorbs orange, it will be transmitting a blue. If it absorbs blue, it will be transmitting a orange. In this particular case, it is absorbing a orange light. So what is exactly opposite to orange? That's blue. And therefore, the complementary color of this compound should be blue, and it is blue. This is a cupric salt. Cupric salt has blue color. Okay. Chalo, moving ahead with this now. You can take a look at it. If you have any doubt, you can ask me in the comment section, obviously. Okay. Chalo, moving ahead. AgCl. AgCl precipitate dissolves in NH3. AgCl precipitate dissolves in NH3 due to formation of. See, it dissolves. AgCl is a white color precipitate. Okay, it's a white PPT. Now it gets dissolved in ammonia. It gets dissolved in ammonia due to formation of a compound. How does that compound looks like? Let me tell you. So AgCl basically is Ag plus Cl minus. As soon as you put ammonia into it, ammonia does what? Ammonia's lone pair starts donating its lone pair to the Ag plus. And there are two lone pair which gets donated to the Ag, which is silver salt, and that gives you AgNH3 to Cl. It gives you this compound, this complex. And this, because of formation of this complex, your AgCl precipitate actually gets dissolved into ammonia. And therefore, the correct answer for that is this, AgNH3 2Cl. It appears that it is in option B also, and it is present in option C also. Okay? But you should understand what it is getting. NH3 2. Okay? Sure. Moving ahead. Next question. Which one of the following compound will exhibit linkage isomerism? See, there have been so many questions been asked on linkage isomerism, especially in a NEET exam. The linkage isomerism, how can you predict or how can you judge the linkage isomerism? See, for linkage isomerism, your ligand should be, it should be able to ligate, it should be able to ligate to a metal through at least 2 atoms. It should be able to ligate to metal at least through 2 atoms or 2 positions. So as far as ammonia is concerned, ammonia cannot ligate through 2 atoms. It can ligate only through nitrogen, through which it donates lone pair. Chlorine is a single atom, so there is no question. This compound cannot show linkage isomerism. However, it can show geometrical. Okay, but that is not they have asked us in the question. Okay. Next, again here ammonia, it can ligate through only nitrogen. But yes, you are a nitro group here. Nitro group can ligate through oxygen. It can ligate through oxygen. Yeah. Secondly, it can ligate through nitrogen also. It can ligate through nitrogen. It can ligate through oxygen. So it can ligate through both the position, and therefore it can show linkage isomerism. That means in one compound, the compound will be ligated to a metal. The metal is cobalt here. So in a one compound, cobalt will be ligated through a nitrogen, and in another compound, it will be ligated through a oxygen. So if it ligated through a nitrogen, how do you represent it? CONH3 NO2 Cl2. Okay. And if it is ligated through oxygen, how do you represent it? CONH3 ONO Cl2. That's how you can represent it. Okay. And both of these two are linkage isomers of each other. That is why this particular compound can show linkage isomerism. Okay. Any other option? Again, this is just like the compound A. Both of them can coordinate through only one side. Ethylene diamine can coordinate through two sides, but both the sides are same. Both the sides are nitrogen only. Both the sides should be different, and then only you can call that compound, or you can say that compound exists in a linkage isomeric form. Okay, I hope you really enjoyed this session. So moving ahead, if you really do, please like this video, comment on it, and please like to practically. Next, a magnetic moment. A magnetic moment of 1.73 Bohr magneton will be shown by one among the following compound. See, let me tell you a trick for it. See, magnetic moment can be found by n plus 2 under root. So mu Bm. Bm is a Bohr magneton, as you can see here. They have written here also. Mu is what? Magnetic moment. And what is n? N is number of unpaired electrons. N is equal to number of unpaired electrons. Okay. So if you put n1, it becomes 1, 1 plus 2. 2 plus 1 is 3. 3 into 1, under root 3. Under root 3 is somewhere 1.73. If you put n is equal to 2, it becomes 2. 2 plus 2 under root. 2 plus 2, 4. 4 into 2, under root 8. Under root 8 is somewhere around 2.73 or 74, something like that. So basically, if the number of electron is 1, n is 1, mu is 1.73. If n is due, it is 2.73. Again, something like that. If n is 3, your mu, if you calculate, it goes somewhere around like 3.81 or something like that. But it is again 3 only. If the n is 4, your mu goes somewhere around 4.89. If your n is 5, your mu becomes 5.92. So you do whatever. It will, this number and this number will always be same. Whatever you have 5 point something after that, but the main digit would always be same, and that main digit can always tell you how many unpaired electrons your compound has. Now in this particular case, your magnetic moment is 1.73 bm, which corresponds this compound to have only single unpaired electron. N is equal to 1. So we need to find out here which compound is having one unpaired electron. Okay, so CuNH3 2 plus. CuNH3, if you find out the oxidation state of copper, ammonia does not have negative or positive charge. It's a neutral ligand. So X plus 0 is equal to charge on complex, which is plus 2. So copper is in a plus 2. The atomic number of copper is 29. So what is its electronic configuration? Argon 4s1 3d10. Out of this, it is copper is in a plus 2. That means you need to remove 2 electrons. So when you remove 2 electrons, it should become argon 4s0 3d9. And how do you arrange the 9 d electrons? You will arrange them as 1, 2, 3, 4, 5, 6, 7, 8, 9. How many unpaired electrons do you have? Single unpaired electron. And that single unpaired electron must be corresponding it to have 1.73 bm as a magnetic moment. And that is why your answer here should be A. It should be A. Now let me tell you for the other species also. We will calculate it for the other species. But before moving to that, let me rub all of this. Okay, sure. Moving ahead. Next, NiCN4 2 minus. Now, if you calculate the oxidation state of nickel here, NiCN4 2 minus. Nickel, suppose it is an X. Cyanide, what is the charge on cyanide? The charge on every cyanide is minus 1, right? So there are 4 cyanides, right? So x minus 4 is equal to minus 2. X is equal to minus 2 plus 4. 4 minus 2, it becomes x is equal to plus 2. So cyanide is in a plus 2 oxidation state. Sorry, nickel is in a plus 2 oxidation state. Atomic number of nickel is 28. Electronic configuration argon 4s2 3d8. And since nickel is in a plus 2, this s2 electron goes. You are remain with what? d8. And how can you arrange these 8 electrons in a d orbital? 1, 2, 3, 4, 5. Okay, let's arrange them. 1, 2, 3, 4, 5, 6, 7, 8. How many unpaired electrons do you have? You can see this is unpaired, this is unpaired. So total there are 2 unpaired electrons, right? So there are 2 unpaired electrons. That means its magnetic moment should be equal to 2.74 or 73, somewhere close. But this is 1.73. So that is why this surely is not our answer, right? I have already told you what's our answer, right? But I'm just telling you how can you do it for the other systems. Okay, chalo. Moving ahead. Now TiCl4. If you take a TiCl4, each chlorine is in a minus 1, right? So 4 chlorine must be in a minus 4, and therefore titanium must be present in a plus 4, right? What is the atomic number of titanium? It's 22. So again, electronic configuration is argon 4s2 3d2. 4 electron goes because it's in a 4 plus. What do you get? Or the 4 electron goes. And this compound would have 0 electrons in d orbital. It should be d0. When it's a d0, this compound should be colorless firstly, and it should also be, this compound should also be diamagnetic. It should also be diamagnetic. It cannot have any electron. I mean, it has no electron in d orbital, therefore this compound should be diamagnetic. It cannot be paramagnetic, right? So if it is not paramagnetic, there is no question of it having any magnetic moment. Okay, so therefore this also is not our answer, as you all know. Okay, let's go for the next. Now the last one, COCl6 3 minus. How can we calculate the oxidation state of cobalt? Suppose it is a X. For each chlorine it's a minus 1, right? For us then 6 chlorine, it become minus 6 is equal to total charge. What is total charge? Minus 3. So X is equal to minus 3 plus 6 is equal to plus 3. So your cobalt is in a plus 3. If you write the general electronic configuration of cobalt, its atomic number is 27. So it's argon 4s2 3d7, out of which you take the 3 electron. It's a plus 3, right? So this electron goes and 1 d electron goes. It becomes 3d6. And how can you arrange the 6 electrons? 1, 2, 3, 4. See, you can arrange 6 electrons like this. 1, 2, 3, 4, 5, 6. How many unpaired electrons it has? It has 1, 1, 1, 1. Total 4 unpaired electrons. And for 4 unpaired electrons, its Bohr magnetism, or I would say magnetic moment, should be equal to 4.89. Therefore, this is also not your answer. And that is why your answer is first. Okay, clear? So that is how you can actually calculate the magnetic moment of a given compound. That is a way. Okay, sure. Moving ahead with the next question. which is right there. Yeah, let me rub this all. Yeah. So what is the name of this complex? See, it is K3FeC2O4. Now, whenever the K3 is there, that means 3 potassium are there. Now, for 3 potassium, the charge is 3 positive, right? Because each potassium hold a +1 charge. So, 3 potassium will hold a 3 positive charge. So, if the charge outside the coordination sphere is +3, therefore, the coordination sphere should hold a negative charge. Okay, and whenever you have a negative charge, that means your ligand is negatively charged ligand. If the ligand is negatively charged, it should always have a ATO attached to it. I would rather say O attached to it. For example, if it's a chlorine, we can call that as chlorido. If it's a bromine, we call that as bromido. If it is NH2 minus, we call that as amido. Just like that. As far as this concerned, you have oxalate. C2O4, 2 minus. This is called as oxalate. But in the IUPAC nomenclature of coordination compound, it is called as oxalato. It is called as oxalato. Then how can we name this? One more thing. Whenever your coordination sphere has a negative charge, your metal's name, the suffix or the ending of your name of your metal should end with the ATE. That means if it's a gold, it's a aurate. If it's a silver, Ag, it's a argentate. For cobalt, CO, it's a cobaltate. For iron, it's a ferrate. For a copper, it's a cuprate. For a acid, tin, it's a stannate, and so on. Okay. As far as this case is concerned, it's a ferrate. Okay. So we have reached, it should be ferrate. It cannot be option A, that's for sure. It cannot be option B, that's for sure. What it remains with? Option C and option D. Okay. Now, of which we need to find out the oxidation state of your metal. Now, let's find that. Now, we all know coordination sphere is having a -3 charge. So, let's find out the oxidation state. Suppose iron is in a X oxidation state. Each oxalate, you can see the charge on each oxalate is how much? It's a -2. And how many oxalate are there? There are 3 oxalate, right? So it is -2 into 3 is equal to -3 charge. -2 into 3, it becomes what? X minus 6 minus 3. X is equal to -3 plus 6. 6 minus 3, it becomes +3. So your iron is in a +3. And in both the option, it is in a +3. In both options, they are saying ferrate. Oxalato are 3 and we should call it as oxalato. So in both the options, they are saying trioxalato. So till here, everything is same. Then what remains? What remains is in option D, they are saying tripotassium. There is no need of that. Because whenever you say oxalato, 3 oxalato, and you are putting a charge on iron, from that you can find out the charge on a coordination sphere. And from the charge of coordination sphere, you can find out how many positive charge are there. You just need to mention which positive charge is there. For example, if it's a ammonium, if it's a potassium, if it's a sodium, whatever it is, you just need to mention the name of it. That is self-sufficient. So in IUPAC nomenclature, you do not mention the number of positive charges ever. And that is why option D cannot be your answer. Your answer should be, and it is potassium trioxalato ferrate 3. That's your answer. Okay. Chalo. I hope you really enjoyed it. Chalo. Moving ahead with this. Yeah. Hexafluorocobaltate. Hexafluorocobaltate ion is found to be high spin complex. The probable hybrid state of cobalt in it. Now this is belonging to BPT. It's the extension of a valence bond theory to coordination compounds. And we need to solve it all that here. We need to solve all that here. Okay, so let's solve it. Hexafluoro. What is mean by hexa? Hexa means 6. Fluoro means it's M minus, and cobalt is in a +3. So they have told us everything here. They have told us it's a high spin also. I'll tell you what is mean by high spin. So it should look like this. CO F6 bracket 3 minus. Because then only -6 + 3. So 6 minus 3 minus 3, cobalt is having a +3. Then only your cobalt can have +3 when its coordination sphere having a -3 charge. So this is that ion. Now they are asking what should be its hybridization. Now to get that, we need to write the cobalt's general electronic configuration first. Cobalt atomic number 27. Electronic configuration is argon 4s2 3d7. Then you have a 4p0. Okay. Now let's write it is in a ground state. How does it look like in a ground state? So you have a 2 electron here. Then you have a d7, right? 1, 2, 3, 4, 5. How do you distribute these 7 electrons here? 1, 2, 3, 4, 5, 6, and 7. And you have a 4p0 as empty. Right? Now your cobalt is in a +3, as you can see from here. It's in a +3. So CO still 27, right? It's in a +3. You are losing 3 electrons now. And where would you lose 3 electrons from? The 2 electron comes from s orbital and 1 electron come from your d orbital. And therefore it should look like this. 4s, I should rather write like this. 3d6, 4s0, 4p0. Okay. Now how do you distribute this d electrons? 1, 2, 3, 4, 5. So 6 electrons will be distributed like this. 1, 2, 3, 4, 5, 6. Right? Then you got 4s, and then you got 4p. Okay. So basically you have 4 empty orbitals. And as far as the ligands are concerned, there are 6 ligands, right? There are 6 ligands. For 6 ligands, you should have 6 empty orbitals. You should have 6 empty orbitals. Now, after 4p, there's one more orbital which I did not mention while telling you this, is 4d0. 4d0 has, again, 5 empty d orbitals. Now look, they have already told us high spin complex. What is mean by high spin? High spin means there is no pairing. There is no pairing by ligand. Ligand does not cause any pairing here. Because fluorine, F minus, your F minus is a weak filled ligand. It's a weak field ligand, and weak field ligand do not cause any pairing. Had there been any other ligand here which is a strong field, suppose there is a amine here, there are 6 amine. Now amines are what? Amines are strong field ligand. What would amine have done? Amine would have done that they have paired, they would have paired this electron. This electron would have paired with this. Let me tell you with the color, another color. Okay, let's take this dark color. Amine would have paired this electron with this, and it would have paired this electron with this. That would have made this 2D empty. That would have made this 2D empty. So 2D empty, 1s is empty and 3p are empty. Now, in that case, the hybridization would have been D2sp3. Okay, it would have been D2sp3, but along with that, this electron would also have paired. When this electron have been paired, you would not have any unpaired electron here. So when the case is that you don't have any unpaired electron, that means spin is what? Spin is less. Then what do you call those complexes? You call those complexes as low spin complex. In fact, it does not have any spin. I should call it as a no spin. Okay, but in some case we might have 1 or 2 electrons. Okay, that is why you need to use the word low spin complex. And low spin complex, it would have caused a pairing. It would have made this 2D empty and sp3. And in that case, hybridization would have been D2sp3. And those kind of complexes are also called as inner orbital complexes. Okay, that was the case when you would have taken, or if they would have given us strong field ligand. In this particular case, they have given us fluorine, which is a weak field ligand. And a weak field ligand do not cause the pairing which I shown you here. The pairing that you are seeing here, it does not happen here. That means electron stays as it is the way I have drawn it. That means these 4 electrons will remain unpaired, making it high spin complex. But you need to make available 6 empty orbital. How would you make it? Then you need to take the outer d orbital. So in this case, you need to take outer d orbital, and that is how you get this 2d orbital. So you get 1s, 3p, px, py, pz, and 2d. That will ultimately give you sp3d2. So here you can see you have taken outer d orbital. Here you have taken outer d orbital, and that is why it is called as outer orbital complex. That is why the correct answer should be sp3d2, which is present in option C in this particular question. That is why, and that is how your answer should be C. Okay. So this is the way. Now we have solved one question only of the VBT, but in the process we have covered the whole VBT. I have told you the summary of the whole VBT here. Okay. Chalo. Moving ahead. I hope you really enjoyed it, liked it. Chalo, moving ahead. I will erase all the inks here now, because I need to solve the next question. Yeah. So the answer for this was this. Now, in the complex NiH2O2 NH342 plus, the magnetic moment of nickel is. Now for that we need to find out the oxidation state of nickel first. So if you draw this compound, oxidation state of nickel is suppose X. H2O is a neutral ligand, so 0. Amine is a neutral ligand, so again 0, is equal to overall charge, which is +2. Therefore, charge on nickel is +2. How would you write nickel? Atomic number 28. Argon 4s2 3d8. Then you are writing nickel +2. So for nickel +2, this electron goes. What remains is 3d8. How do you distribute this 8 electrons? 1, 2, 3, 4, 5, 6, 7, 8. So you got 2 unpaired electrons. These are the 2 unpaired electrons, right? So for 2 unpaired electrons, we know that magnetic moment should be 2 point something. And 2 point something dollar option is only one. It's B, right? And therefore your answer here should be B. Okay. Now we have solved couple of questions of this category. Okay. So it should be quite easy for you to calculate it now. Okay. Chalo, moving ahead with this question. Next. A complex shown below can exhibit what kind of isomerisms? See, this compound is of the type M, A, B, C, D, E, F type. It is this type of compound. You can see that clearly. This compound can always show optical isomerism. It can show optical isomerism. Yeah, definitely. How? If you have drawn this compound, suppose if I take the mirror image of this compound, if you take the mirror image of this compound, this is our mirror plane. If you take the mirror image of this, it should look like, you would have a F here. Now, okay, it's a mirror now. If it is like this, it should look like this. So F is there, E is there, okay, C is here, B is here, right? And your A and D would be unchanged. Now, try to lift this compound and try to place it over its mirror image. Try to lift this compound in the option and try to place it over the mirror image. Does it get imposed? Does it get superimposed? No, it will not get superimposed. And that means this compound is asymmetric and therefore it should show optical isomerism for sure. And this compound does show optical isomerism. Now, apart from that, what we are remain with? Geometrical isomerism. Geometrical isomerism. Does it show geometrical isomerism? Yes, this compound does show geometrical isomerism. See, in this compound, you have A and B here. Okay. Suppose if we classify that A and D are of the same type. So when they are opposite, they are trans. When D comes in the position of B or F, it will be called as cis. If it goes opposite, it will be called as trans. So they can be categorized as geometrical isomers as well as optical isomerism. Therefore, this compound can show both optical and geometrical isomerism. Okay, it can show both the isomerism quite easily. Okay, sure. Moving ahead. Theoretically, the number of geometrical isomers. See, I just saw this question, right? M, A, B, C, D type. See, M, A, B, C, D, E, F. That means you have a central metal in a hexa coordinated system. In a hexa coordinated system, which generally is called as octahedral only. Okay, 6 coordinated system generally is always octahedral. Now in this octahedral, every ligand is different. A, B, C, D, E, F, all the ligands are different. Okay, and such a type of compound can show 15 geometrical isomers. I mean, basically it can show 30. Technically, it can show 30 isomers, out of which 15 are cis, 15 can be called as trans. And that is why we can say theoretically it can show 15 geometrical isomers, however, of which only 2 or 3 has been isolated. Okay, so that is why I'm saying theoretically. Practically only 2 or 3 have been isolated. We don't know about the other isomers. Okay, so next, which of the following has 2 geometrical isomers and is also a non-ionizable complex? See, non-ionizable complex, all of these things comes from the Werner's coordination theory. It comes from Werner's coordination theory. And what does this theory says? Suppose if you have a ligand like this, M, A3 and B3. Then this B3 are ionizable if they are. They are ionizable if they are, and this is non-ionizable. It is always like that. Let me give you a simple example of it. See, cobalt, coordination number of cobalt is 6. So CuNH3, CuNH3, I should write 6 actually, CuNH3 6, Cl3. If you talk about this compound, these 3 chlorine are ionizable. These 3 chlorine are ionizable, and if you put aqueous AgNO3 into this, if you put aqueous AgNO3 into this, it should give you 3 moles of AgCl. It gives you PPT, 3 moles of AgCl, because you have 3 chlorides outside the coordination sphere. They are in the ionization sphere. But this compound has one of its isomer, which looks like this: CuNH3, Cl3. Outside of it, they have NH3. Now this NH3, this is in the ionization sphere, but ammonia cannot be ionized. So it is as good as non-ionizable. And as far as this chlorides are concerned, your chlorides are present in a coordination sphere now. So you cannot ionize. You cannot ionize this chlorine. They are now non-ionizable. Now suppose if you put AgNO3 now, suppose if you put aqueous AgNO3 now, you would get no PPT, because chlorides are in the coordination sphere now. Chlorides are present in the coordination sphere. Okay, so overall you need to have at least one chlorine outside the coordination sphere for compound to be called as ionizable. If all the chlorides are inside the coordination sphere and the ligand which is present outside the coordination sphere is neutral, the compound becomes non-ionizable. Okay, now so I hope you must have been clear with this. Let me rub this down so that I can tell you the other things. Okay, yeah. So let's look at one by one. See, the coordination number for platinum in this particular case is 6. And firstly, you need to arrange these compounds. Then you can arrange the other compound. Okay. So if you arrange two ammonia are inside NH3. Outside of which you have 4 chlorine. So all the 4 chlorine are inside the coordination sphere. So this compound should be non-ionizable, and it is non-ionizable. Let me tell you the other example. So firstly, what you need to do? Firstly, you need to arrange platinum, ammonia ligands around the platinum. Then whatever vacancies are left there, I mean, suppose if you have a 2 amine, then you are remain with what? 4 vacancies. 6 minus 2, 4. Here you have a 3 ammonia. That means 3 vacancies are there. So 3 vacancies should be satisfied by 3 chloride, NH3, 3, Cl3. 1 chlorine is remain. It goes outside the coordination sphere. And therefore now this is ionizable. It is ionizable, right? Same case here. How many amine ligands are there? 4, right? 4 ligands are there. 2 vacancies are there. 2 vacancies satisfied by Cl2. And other 2 chlorine must be outside. That is also ionizable. As far as this case is concerned, you got all the 6 amines attached to platinum. And all the chlorine are outside. This is also ionizable. So B, C, D, all of them are ionizable. Only option which is non-ionizable is first, and therefore A should be your answer in this particular case. Okay, that's how you can solve this kind of questions. Next, one among the following complex ions will not show optical activity. See, let me tell you one more point. The compound which shows optical activity, the compound which shows optical activity should have, or I would rather say, I should not call it as a should. I would rather erase this. Okay. The compound showing optical activity generally have what I should say multi-dentate ligands, or I should say chelating ligand. They have chelating ligands. And what is mean by chelating ligands? The ligands which are bidentate, tridentate. That means any ligand apart from monodentate ligand. Any ligand, hear my words carefully, any ligand apart from monodentate ligand. That means bidentate ligand, tridentate, tetradentate, pentadentate, hexadentate, heptadentate, octadentate, whatever number of dentate you take apart from mono, all of them are chelating ligands. And chelating compound to have a chelating ligand is a prime condition for compound to show a optical activity. Okay. However, some compounds do not show optical activity despite they are having a chelating ligand. For example, let's take this case. This is a cis they are telling us, right? So if you draw this compound, it is a cis. How should it look like? See, it should look like this. Let me draw all. It's a, what is it? It's a octahedral, right? So N. So this is nitrogen, and you have a chlorine on this side. So this is how it looks like. If you take its mirror image, now you need to, what I should say, you need to visualize it. Okay, you need to imagine in the air. If you take a mirror image of it, you will have those loops of two nitrogen on this side, and you will have chlorine on the right hand side. If you take this compound, if you lift it, and if you try to keep it over that compound which is formed after the mirror image, you would observe that both the compounds are not superimposable. That means this cis part can show or does show optical activity. Okay? Let me tell you the trans example of it. Okay? Then you will understand what I mean to say. Nitrogen. We have a nitrogen. And then you have a chlorine. Now take the mirror image of this. Now imagine in your head, take the mirror image of this. See, you will get the same compound. If you take the mirror image of this compound, you will get the same compound, and it is the same compound. You can see this compound is trans. These two are, what I should say, they are geometrical isomers of each other. So this is a trans and it does not show any optical activity. Okay, the molecular formula is exactly same. So that is what I meant when I was telling you this, that this compound does have a chelating ligand, but it does not show optical activity because it is a symmetric compound. So yeah, you need to have a chelating ligand, that's fine, but having a chelating ligand would not guarantee compound to have a optical activity. Okay? As far as this concern, they are asking one among the following complex ion will not show optical activity. So it is not that. B is showing optical activity. This compound, would it show optical activity? Yes, it can be asymmetric. As far as this D are concerned, yes, this can also show you optical activity. This compound, BrClI2C2H5NNH3, this compound is of type MABCDEF, and this compound do not show any optical activity for that matter. Okay, sure. So I told you this thing. I need to rub it down for you to understand the next question. Okay, so moving ahead. Now, what is the next question? The next question is a planar complex. A planar complex MABCD gives how many isomers? Optical isomers, it does not show optical isomers. It does show geometrical isomers. But how many of them? Let me show you. So they are saying planar complex, right? So planar complex do not show optical activity anyways, because planar complexes are, they are, what I should say, they are symmetric. They are symmetric, and symmetric compounds do not show optical activity. So no optical activity. So, but they can show geometrical isomerism. Okay, so let's draw them one by one. M A B C D. It's a square planar, right? It's a square planar like this. So what do you do now? You keep the A constant and rotate the other ligands. You keep the A constant at its position and rotate the other ligands in a whatever manner. Let's suppose this, you are rotating this in a clockwise manner. Okay? And let's see how many geometrical isomers can be obtained. So B goes to C position, C goes to D position, D goes to B position. D cannot go to A because we are keeping A constant. Okay, so it should give us A, D. Then you have a B and you have a C. So this is the second ligand now. Sorry, second compound. Now again you are rotating clockwise. What should you get? D goes to B, B goes to C, C goes to D. So you get A, C, D and B. Okay. Now if you rotate this compound again, in a clockwise manner, you should get what? You can imagine, so you can visualize yourself. If you rotate this again, the A will stay there, but now B will come to its original position. See, C will go here and D will go its original position. So you will get your original compound back. And you cannot consider this in counting. So how many geometrical isomers are you getting? 1, 2 and 3. So you are getting 3 geometrical isomers, and that is why 3 geometrical isomers are where? Yeah, it's present in D option. And that is why our answer should be D here. Okay. Chalo, I hope you really enjoyed this session. Chalo, moving ahead with this, which gives only 25% mole of chlorides, which gives 25% mole of chloride as AgCl when reacts with AgNO3. So 25% mole of AgCl when reacts with AgNO3, that means the compound is having 4 chlorides and it is giving only 1 chlorine, because 25% means what? 25% means out of 4, only 1 chlorine is going with the AgNO3 in the form of AgCl. What does that mean is that only 1 chlorine is outside the coordination sphere and other chlorine must be present inside the coordination sphere. Okay, so we had seen a couple of slides ago how to check how many chlorides are there. So as I told you earlier, first write the ammonia ligands and then make a total count of 6 inside the coordination sphere. Whatever remains, put that outside the coordination sphere. As far as first option is concerned, you got 4 ammonia. So only 2 vacancies are there, which can be substituted by 2 chlorine. And everything finishes. There are no chlorides remain here. So this basically cannot precipitate silver in the form of AgCl at all. Okay, firstly, this cannot give you that. So this cannot be an answer for sure. Next one is this. For this compound, you have PT, 5NH3, 1 chlorine. As I told you, we need to make a total valency 6 in the coordination sphere. 3 chlorines are still there. Out of 4, 3 chlorines are there. So if these 3 chlorines are outside the coordination sphere, that means all of them can get ionized. And in that case, it would be 75%. It is not 25%, right? So that cannot be your answer. So that goes. Next is this one. As far as this is concerned, again PT, NH3, 4, 2Cl2, 2Cl2 are remain, they are outside. So if this whole Cl2 are outside, they can get ionized. Out of 4, 2 are getting ionized, that means 50%. So this also can be your answer. Lastly, if all of these 3 are not your answer, D should be your answer, that's for sure. But let's see how. The 3 ammonia ligands inside, other 3 valencies are satisfied by 3 chlorine. So out of 4, 3 chlorine comes here, 1 chlorine remains, which stays here. That means this 1 chlorine can get precipitated with the AgNO3 in the form of AgCl. So out of 4, only 1 is going, which is 25%. And that is why, and that is how this should be your answer. Okay, chalo, moving ahead. Which of the following compound is paramagnetic? Which of the following compound is paramagnetic? Now, what is mean by paramagnetic? Compounds having unpaired electrons. Compound having unpaired electrons are called as paramagnetic. Now, we need to check out of these 4, which compound has at least 1 unpaired electron. The very first, tetracyanonickelate. Now, tetracyano, that means 4 cyanides are there. Nickel is there. And what is charge? Tetracyano. Now, we don't know what a charge here. We need to find that. Nickel is in a +2 oxidation state. That is what they had told us. And we need to see only that thing. Okay? Because we need to check whether it has at least 1 unpaired d electron or not. So this is nickel is in a +2. Atomic number of nickel is how much? 28. So argon 4s2 3d8, out of which s electron goes. D8 system is there. So D8 system has at least 3 unpaired electron. Okay, let me tell you how. How can you arrange 8 d electrons? 1, 2, 3, 4, 5, 6, 7, 8. See, it has at least 2 unpaired electrons. So it can be your paramagnetic species. Okay, but we need to check whether others are not. Tetraamine zinc 2 ion. Zinc is in a +2. That's for sure. They have given us already. Atomic number of zinc is how much? It's 30. Argon 4s2 3d10. So it's a +2, no? So this 2 electron has gone. It's a D10 system. D10 system has no unpaired electron, right? You must have understood that much over the period of 2 years of your study now, right? So it is obviously diamagnetic. Then you have a hexaamine chromium 3. So chromium is in a 3 oxidation state. Atomic number of chromium is 24. Argon 4s1 3d. Argon 4s1 3d5. Chromium is in a +3 oxidation state, right? As they have told us here. 1 electron from S, 2 electron from D goes, and it becomes what? D3 system. And D3 system, that means having odd number of D electrons, should always be paramagnetic. And it is paramagnetic. Okay, but let me tell you some other things. As far as tetracyanonickelate is concerned, so let me tell you the strong field and weak field complexes. See, your nickel in this particular case was having 8 electrons, right? That we already found. Now, how can you distribute those electrons? That is what the question is all about. See, nickel is with the cyanide, and cyanide is what? Cyanide is strong field ligand, and strong field ligand does what? It causes the pairing. It causes the pairing of electron. So these 8 electrons, as you have arranged here, they will get paired. This last electron gets paired with this, and now you have 8 electrons like this. So there are no unpaired electrons here, which makes your nickel to be not para, diamagnetic. Okay, because cyanide was a strong field ligand. Okay, now let me tell you why I'm saying, let me rub this. We have already solved this, right? Yeah. So why I was saying chromium 3 is paramagnetic, because chromium has 3 electrons. So how do you distribute 3 electrons in d orbital? 1, 2, 3, 4, 5. You distribute them like this. 1, 2. Now your chromium is attaching with the amine. Amine. See, this is amine. Amine is what? NH3. And NH3 is what? NH3 is also strong field ligand. NH3 is also strong field ligand. So it also causes pairing. It also causes pairing. So it causes this electron to get paired with this. But even if it gets paired, you still have one unpaired electron. You still have one unpaired electron, and that would make it paramagnetic. So basically, even if you have a strong field ligand, if you have an odd number of d electrons, it would always make you paramagnetic. And that is the way you can find out whether given compound is paramagnetic or not. Okay, so moving ahead. Now, the last 2 questions of today's session. Okay, which of the following will give maximum number of isomers? Which compound would give you maximum number of isomers? Now we need to calculate it. So this is Ma4B2 type. So Ma4B2 type, this compound can show you like this. Ma, A, A, A. You have a B. This is what? This is trans. How can you write a cis? A, A, A. You got A, B, B. Right? So this is your cis trans geometrical isomerism. This compound cannot show, the trans wala cannot show optical isomerism because it is a symmetric complex. But this compound, if you take a mirror image of it, it can show optical isomerism. It can show optical, it can show geometrical. So this 1, 2, and what I say optical. So there will be one more isomer on 8. So it can show 3 isomers overall. It can show 3 isomers. If you take an example of this compound, it cannot show geometrical isomerism. Why? Because the point of attachment with the nickel, all of them are nitrogen only. See. Ethylene diamine. So you got only, you got only one ethylene diamine. Okay, then you got what? NH3, 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 NH3. If you take a mirror image of this, because of this, it will show optical isomerism, but it cannot show you geometrical isomerism because there is no difference in the point of attachments there. So it can show you 2 geometrical isomers. So 2, this one. This can show you NiC2O4. So it is just like, if I draw it, it will be like this: N, M, N, N, Okay, then you have a N, sorry, N like this. This cannot be present there. Then you have a oxalate O. Okay, so this, and then you will have a optical isomerism of it. So it can show you two optical isomers overall. Lastly, you got a SCN. So whenever you have a SCN there, it can show you linkage isomers also. Why? Because SCN, your HCN can linkage through sulfur, or or it can linkage through nitrogen also. So those are the two isomers. Which two? Two linkage isomers, and it is of MA4B2 type, which we saw here. See, MA4B2 type. So it can show you three isomers. Out of those three, two will be geometric isomers, one will be optical. So two linkage plus three geometric and optic. Overall, it can show you five isomers. And if you survey all these compounds, you can see clearly this compound is showing you five or giving you five isomers. And that is what our question was. Which of the following compound is giving us maximum number of isomers? And that is why our answer here is D. Okay. Sure. Moving ahead. I hope you must have enjoyed this session a lot. Last question. In the complex ApH2O6 3 plus En3 plus this, the more stability is shown by. See, always remember the chelating ligands. Chelating ligands forms more stable complexes. Chelating ligand forms more stable complexes always. They always form more stable complex. Okay. So H2O6, this is a monodentate ligand. FeCl6 has a chlorine, it also monodentate ligand. So these two are not in the question at all. This goes. Now what remains? We are remain with ethylene diamine and C2O4. Both of them are chelating ligands. C2O4. How does C2O4 look like? It actually look like this. C double bond O. C double bond O. Oh, let me O minus and O minus. That is your oxalate. That is called as C2O4 2 minus. Then your ethylene diamine. How does ethylene diamine look like? NH2, NH2. Then you got CH2 attach here. And through nitrogen, it can coordinate to your metal like this. Here also through oxygen, it can coordinate to the metal like this. Now, the question is which can make the complex more stable? See, it all depends on your tendency to donate the electron density. As far as nitrogen in the ethylene diamine and oxygen in oxalate is concerned, the nitrogen is less electronegative than oxygen, as we all know. And because of which, nitrogen can donate the electron density more easily and hence make the complex more stable. And that is why in this particular question, the answer is B. Okay. And that's it for today's session of NEET crash course. Okay. I hope you really enjoyed this session. If you do, please like and comment on this video. You can subscribe to Practically Live on a YouTube. We have very interesting courses for you. If you really want us to bring more such interesting courses, please like, comment and subscribe to Practically on YouTube. And you can also download our app, which is named by Practically only, from Play Store and from Apple Store. Okay, you can download it from there. You can log into it. You can check different courses in robotics, Vedic maths. Then we have courses in coding. Okay, you will really enjoy those courses. Okay, we have a special offers also for you there. So please go and check it. Okay, that's it for today's session. Bye bye from my side.